Hey guys, Mr. Betts here. Let's take a look at an example where we want to find the area of a region bounded by functions. And in this example, we want to write two different expressions involving integrals to find this area. And this is an example of one where there's actually lots of different ways that we could do this. So when it says two expressions here, we're looking for one with respect to x and one with respect to y. So first thing I want to do is get an idea of what this region looks like. First of all, we're going to be in the first quadrant. So we're looking just up in this region here. We know what the square root function looks like. So y equals the square root of x is going to look something like this. And we know that this other function is going to be a line with a slope of 1 and a y-intercept of 2. So with a y-intercept of 2, it's going to look something like this. So that may not be perfectly drawn to scale, but it does give us an idea, and the region is going to look something like this. So with respect to x, let's first kind of picture what a Riemann sum rectangle is going to look like. And we'll notice here that in two different subintervals, we're going to get Riemann sum rectangles that are bounded above and below by different things. So above is always going to be the square root function, but below for part of it is going to be the x-axis and the other part is going to be that line. So we are going to have to split this up into two separate integrals. And in order to do that, we're going to need to know what our limits are going to be. So for that, we need to know the x-coordinate here, and we're going to need to know the x-coordinate here. So for the first one, where that line crosses the x-axis, we're looking for where this is equal to 0. So that's pretty straightforward algebra. We just say x minus 2 equals 0, and that's going to be at x equals 2. For the second one, that's going to be the intersection of the two functions. So it's going to be a little bit more complicated. It's going to be where the square root of x is equal to x minus 2. I'm not going to go through all the algebra. You could probably guess, especially if you graph this pretty accurately. But we could square both sides. So we get x equals x squared minus 4x plus 4. Subtract the x to the other side. We're going to get two intersections. One would represent the one that we're looking for, and the other one would represent an intersection that would end up down here. Let me get rid of that. But the one that we're looking for here is going to be at x equals 4. You can confirm that by plugging 4 into both. The square root of 4 is 2. 4 minus 2 is also 2. So using those, we're going to write an integral expression with respect to x. And this is actually going to involve two integrals. Like I said, the first subinterval from 0 to 2 is going to have that square root function on top. And on the bottom is just going to be the x-axis. Now we can write the minus 0 there if we want, but we don't need that. So that's just going to be the square root of x with respect to x. And actually now those square brackets aren't necessary. So that's going to give us the area on that first subinterval where the square root is on top and the x-axis on the bottom. For that second subinterval going from 2 to 4, the top function is going to be the square root of x, and the bottom function is going to be the x minus 2. So this expression involving integrals with respect to x will give us the area of that entire region. Now let's switch perspectives here and look at this with respect to y instead of x. So if we're looking at this with respect to y, our Riemann sum rectangles are going to be horizontal rectangles. And we can see here that all the way from the lowest y value here to the highest y value here, the line is going to be on the right and the square root function is going to be on the left. So since the right and the left do not change, we're going to be able to write this as a single integral. So to do this, we're going to need lower limit and upper limit. And in this case, our lower limit and upper limit are going to be along the y-axis. So the lower limit is going to be 0. The upper limit is going to be the y-coordinate of this intersection. So if the x-coordinate is 4, we can plug 4 into really either one of these. So plug 4 in here or plug 4 in here, and we get a y-coordinate of 2 for that point. So that's going to be our upper limit. Then when we write our integrand, we want to do right minus left, but we have to do this with respect to y. So for both of them, we're going to have to solve for x and write x in terms of y. So the right one is going to be this y equals x minus 2. And solving for x is pretty straightforward. We add 2 to both sides. We get x equals y plus 2. So that's going to be our right function minus the left. So the left is going to be the square root, y equals the square root of x. To solve that for x, we're going to square both sides, and we get x equals y squared. And then our Riemann sum rectangle, this expression here gives us the width of any given rectangle. The height of any given rectangle is going to be dy. So this, I need to write this all in one color. That's going to bother me. This integral expression here gives us the area of that region with respect to y. Now, I've talked about this in a previous problem, but having written two different expressions, now we can choose one that's simpler to evaluate if we actually had to find the area. This problem's not asking us to do that, but if we did have to evaluate one of these, this expression right here is much easier to take the antiderivative of and to find the area of. The expression with respect to x, we're going to have to do antiderivative of square root of x, which is not difficult, but it is going to involve fractional exponents. And we're going to have to evaluate two different integrals. So with respect to y, this allowed us to write it as a single integral, and a single integral that's easier to evaluate.